Last class we discussed that uh, we discussed the theory about the slope stability part, and we did some questions on the earth pressure topic, and we are to do in fact some we are to do some questions on slope stability in this class. So half of the class we will do some questions, and then we can have an interactive session. And if you have any question, if you have any doubt about the entire any topic from the course, you can ask that. Even if because I can see many new faces that have joined today, because this maybe because this is the last class. If you want, we can have a question answer session first, and then we can move further with questions on slope stability. If you have any doubts, you can ask me. If you're stuck somewhere, we can have that first, and then we can continue with the questions, or we can start with the questions and later you can ask the doubts. Is it up? It's up to you. So, how would you want to proceed in the class? Any suggestion on how we should proceed? If
Ma'am, I think uh, can we please continue with the session, and after that we can have some question and answer session also.
yes, sure. So, in last class that is now available on YouTube in your in the playlist with the other classes. In the last class, we talked about the different methods of how we calculate slope stability, why it is one of the core topics for our, so what we discussed. We say it this way. In soil mechanics, whatever you have studied till now, that comes under either classification or properties of soil, basically behavior of. So we study about the behavior of soil, like your index properties, your engineering properties, and you have the methods, y- the behavior of soil under like consolidation, or the behavior of soil in terms of what is its shear strength. But the reason for us to do this is so that we can predict behavior of soil. So I have a land and I want to build a building over it. One type of geotechnical question that you can have is, I want to build a building over it. I know what the total weight of the building will be. So geotechnical engineering will help me to firstly determine whether this building will hold over this soil or not, which comes under the bearing capacity problem. Second thing is that if um, um, and what kind of foundation I need to provide, if it is weak, if it is strong, the soil underneath. Second thing is, if it is not strong enough, what kind of soil improvement I can do for to be able to make this construction. And the second type of geotechnical question you will get is with respect to slopes. These can be hills, these can be mountainous slopes, these can be natural, man made, Man-made slopes are your cuts on excavations that you make, or slopes that you create for maybe like along a mountain, incorporate a road or something. And natural slopes are just your mountains and everything. So you study the stability of the slope. In these slopes also you get two kind of questions. First, you want to know if the slope is stable. Second, you want to know if you want to do any construction on the slope. So the second part is not what we are studying right now. What we're studying is the stability of a slope. The slope can be natural, it can be man-made. What all we need to know uh, is is the slope stable? Like, oh, you get landslides and you get all those things. Failure. So these are the types of failure you can have. You can have a rock fall. This is also a kind of slope. You can have toppling. Usually this happens in rocky slopes. When you have rocky, most of you don't know, but rock mechanics also comes under the, because we don't study it much. It also comes under the ambient of geotechnical engineering, in which we study, because most of the, we can say, the theories that we apply to soil, we can apply them or rock also. So we assume rock to be porous, but they are, those pores are microbial, like very microscopically fine. So you have rocks in this kind of manner, and if even one of the rocks i- will fall like this, you will get domino kind of effect, and all of this will come toppling down. This is called the toppling. This is a general failure of soil. When you have a slope, you can have a body, a slip surface in this manner, which tends to rotate about its center of gravity, and you get a failure like this. And then you have, so this is like a slope failing by lateral spreading, like in over a period of time, you will see that cracks will fall in this direction. This is, and this is kind of a landslide kind of failure if material is. So we will be talking about this kind of failure, and we discussed the theory behind this kind of failure in the last class. But I would like to discuss a bit more on factor of safety and what are the types of factor of safeties that we consider in slope stability. So, what are the types of factor of safety that we consider in this slope stability method? So, the first of all, we need to know the definition of factor of safety. Then we take the stability of infinite slopes, stability of finite slopes with plane failure, stability of finite slope with circular failure, and we analyze the stability of finite slopes with steady state condition. So these are the main topics that you might have to cover in slope stability. I would like to discuss the factor of safety for the types. The easiest basic formulation for safety is the ultimate strength over mobilized strength, shear strength. This is the average shear strength of soil or average shear stress developed along tensile failure surface. So we have a soil and you believe that there exists a failure surface along which the soil can fail. So the factor of safety will be the strength of the soil you will get from its characterization, your lab testing, like the maximum load that the soil, maximum strength of the soil you will get from your triaxial test, you will get from your direct shear test, let C5 values, and from there you can calculate sigma tau is equal to sigma plus C plus sigma dash tan phi. You know? So this is your strength, absolute strength. But this thing, the average shear stress developed along the uh, failure surface, this depends on the nature of the slope. How much stress is actually developing will depend on the nature of the slope. Now, if I take one factor of one failure surface, I calculate the tau d along this failure surface, and then I calculate the factor of safety by tau f by tau d. This I know, this I calculated based on your slip surface. Okay, but you can have multiple types of slip surfaces, isn't it? And all these surfaces will have a different factor of safety, isn't it? So the critical factor of safety will be the minimum factor of safety. So uh, if you fix the value of factor of safety and you know the strength of soil, you can calculate how much the how much shear stress can be allowed on the what will be the critical shear stress beyond which the soil will fail. And the critical shear stress that you calculate, based on this you can fix the minimum height of the slope that you're required and uh, all those things. Okay, so that is one way of approaching this, and this is based on the total shear strength. Other way of defining your factor of safety, let me write it like this. So we write this, let's write this as tau d or mobilized. Okay, there are different ways in which you can calculate this tau d, and that is why I will not expand upon this. Second factor of safety, second type of factor of safety that you can define is if you define tau d as C dash m plus sigma dash tan phi dash m, where C dash m is mobilized cohesion and phi dash m is mobilized friction. So what we are doing here is we are defining the tau in the same manner as we defined the total strength. But what we are doing is that if the uh, cohesion at failure is C and the friction at failure is phi, and right now only some of that strength has been mobilized. So if we calculate the Cm and we calculate the phi m, then we can calculate tau as this. The second type of factor of safety that we come across is due to cohesion, that is C dash m over C dash. Okay, sorry, C dash over C dash m. And the third type of factor of safety is the friction due to friction, and that is tan of phi over tan of phi m. Okay, so these are the definitions of factor of safety that we use. And when we compare FC by FC equals C dash over C dash D, F phi equals tan phi over tan phi D. So if FC is equal into F phi, then your Fs equals C dash plus sigma dash tan phi dash over C dash m plus sigma dash tan phi dash m, isn't it? And we can write this as, we can write C dash as Fc times Cd and tan phi dash m as m. F phi times tan phi m. If we substitute it here, we get Fc dash Cm plus sigma dash into F phi times tan phi m over Fc Cm dash plus sigma dash tan phi m dash. And because Fc equals F phi, that is what we had assumed in the beginning. So this will be common and this will get um, cancelled out. We will get Fs is equal to Fc equals F phi. If we take Fc equal F phi, we will get this factor of safety with respect to shear stress to be equal to, like all of these factors will become equal. So usually what we do is we take the minimum factor of safety from these. So let's do a question. I just wanted to uh, discuss this very briefly. So for the infinite slope shown, consider that there is no seepage through the soil. Determine the factor of safety against sliding along the soil rock interface. So this is the rock interface, and so what we are necessarily saying is that this is the failure the on failure surface, what we need to calculate is the factor of safety along this. The height h that will give factor of safety of 2 against the sliding along the top. So these are the two ways of uh, approaching problem in slope stability. First thing was we wanted to calculate that what is the impending failure, what is the condition of the impending failure of a particular slope. Will the slope fail or not? Usually this we do for slopes that we want to build. Obviously, a slope that is already present will not fail on its own unless there is some external force on the slope. We can calculate what kind of force will make the slope fail. But a slope that is already existing, a hill, any kind of slope that is already existing, you know that it will exist and will not fail until an external force is applied. So this kind of problem we solve when we have to build a slope. So factor of safety against sliding, because um, what we do here is I propose a 15-degree angle for the slope, and then I calculate the factor of safety, and I assure that factor of safety should be greater than 1.5. If the factor of safety is greater than 1.5, I'll say okay, let's go forward with the developing the slope. The second kind of problem is the height that will give a factor of safety to against the sliding rock. So the second kind of problem is like you want a specific factor of safety, and you are kind of uh, deciding based on a particular value of factor of safety. Okay, so can you start with solving this question? Give me just 5 minutes. I will be back in 5 minutes. Please start with solving this question. I will discuss it as I come. Okay. uh, started with the question, you can let me know. Otherwise, we can start solving the question. How do we define the safety here? For example, safety will be your strength, this is equal to sigma dash plus. So, as you already have covered how we calculate sigma is a this is basically the normal stress. So what we need to do is the resultant weight of the slope is acting along the force of direction of gravity, and the resolved forces of normal and tangential forces we will have like this. So what will be the normal force? This here will be equal to beta. So the normal force will be W times W cos theta, cos beta, and F tangential will be W sin beta. And the stress in the normal direction will be, we have to take into consideration the this area, inclined area. Let us say that this is 1 meter in this direction. So corresponding to this L, what will be the, this is a slant height and uh, normal height. So corresponding to slant height, this basically will be, this is L and this is H. Corresponding, uh, this height will be,
Ma'am, can't we solve this at tan phi by tan beta?
huh?
Ma'am, tan phi by tan beta for the factor of safety.
Tan phi by tan beta. Not actually, because this has a C value. Tan phi over tan beta we only take for um, uh, cohesionless soils, purely cohesionless soils that don't have a C value. What about the C value? Hmm?
Okay, ma'am.
So if we take a section here, this here, this was the weight, and this was your normal, and this tangential component. This is your L, this is your H. Okay, so the value of L will be, so the slanting height will be L dash, let's say, be L by, and your sigma dash will be your normal stress by area of base. This will be your weight into cos beta over L by cos beta into 1. This will be weight into cos. So sigma dash is weight into cos square beta. And from the equation itself, you see the tangential force that uh, uh, the tangential component of the force. From there, we can calculate the mobilized shear strength, how much shear force is getting generated inside the soil block, which will be W sine theta over L by cos beta. This will be W sine beta cos beta. Okay. And your factor of safety, which was your shear strength, which is C dash plus sigma dash tan phi over your tau, which is basically your W sine beta cos beta. This is C dash plus sigma dash is equal to W cos phi. So W is gamma times H, isn't it? Uh, into L. Wait, H into L into your density will be your W. So this can be written as gamma H L sine beta cos beta. This will be gamma H cos beta sine beta. And same way, this will be gamma H cos square mm, gamma H cos square beta tan phi over gamma H cos beta sin beta. Write this as C dash over gamma H cos beta sin beta plus gamma H cos square beta tan square beta tan beta tan phi, sorry, over gamma H cos beta sin beta. So what we will get is C dash over gamma H cos beta sin beta plus tan phi over tan of beta. So what you were saying, tan phi over tan beta, if C was 0, we would get factor of safety equal to tan phi over tan beta, isn't it? And we can say cos of 2 beta is equivalent to sin beta cos beta, 2, I think something like that.
Sin 2 beta equal to 2 sin
Sin
beta
cos 2
into
beta, huh? Yes,
sin 2 beta equal to 2 into sin beta into cos beta.
was it
Yes, ma'am.
sin 2 beta or cos 2 beta?
Sin 2 beta.
So what we can do here now is we can calculate based on the formula that we just oh, F equals C over gamma H cos beta sin beta plus tan phi over tan beta. This will be 10 over gamma has been given 17.8, 6 cos 15 sin 15 tan 20 and 15. Calculate this. So the factor of safety comes out to be 1.7. The second question is what should be the height that will give a factor of safety of 2 against sliding along the interface. So we will say that factor of safety is 2 and 10 over 17.8 in H into cos 15 sin 15 plus tan 20 over tan 15. Calculate. Get 0.6415 equals 10 over 17.8 into 15 5H H equals 10 over 0.6415 3.5 meter. So if we had assumed that this failure will take place along this surface, then factor okay. So if failure was taking place along a depth of 3.5 meter, then our factor of safety would have been right now our factor of safety at 6 meter is 1.7. Okay. This, yes, please. Is there any question?
No, ma'am.
Anybody who has a question? You can see. I think which you were calculating using only the tan theta, tan beta, and tan phi. Because this is a C5 soil, we need to calculate using both C and beta phi. So this is one type of question that you can get. This is infinite slope failure. This is the master formula for that. Any question that you get from here will be solved from this time. Second kind of question is your planar failure in soil. So there are two kinds of failure surfaces that we assume. One is we assume a circular surface, and we can assume a planar surface like this. So this is called the Kalman's method. Basically, the entire basis of slope stability is you take a slope, and the stability of the slope will depend on the weight of the block that is above your failure surface. So what are the things that you need? You need to do a failure surface. As we saw that we can take a parallel failure surface in infinite slopes. We take a planar surface. Sometimes we take circular surface, and all of these are trial and error method. We take a surface, we calculate the factor of safety, take another surface, calculate the factor of safety, take another surface and factor of safety, and factor of safety critical will be the minimum factor of safety. Okay. So the second thing you need to check is, the first thing is you need a failure surface. Second thing is you need to check how you define your factor of safety. And in all of the methods, what you do is you calculate the weight of the swedge, you resolve it into horizontal and vertical directions, and then based on that, you calculate that the tangential force is the driving force, the normal force is the stabilizing force. From there, you do all the rest of the calculations. This is what we did here also. We took this failure plane, we took this failure wedge, we calculated its weight, we resolved it in normal and tangential direction. That is what we are doing in every method. So in this method, we take a plane or planar failure surface. So so the Kalman's method says that the the Kalman's method says that the slope fails in a planar failure plane if theta b is the angle of the slope. There can be a critical theta below which you will see that the soil will fail. Uh, the failure plane will be like failure plane will be defined such that the shear strength will be just equal to mobilized stress. Okay, so what we need to do is we need to calculate the theta of this slope. The weight of the wedge equals simply half of base BC in H. Uh, this is area of this wedge multiplied by 1 in this direction multiplied by gamma to get the density. So area, sorry, this is the volume multiplied by density to get the weight. So how do we calculate BC? BC will be we can say this is A, mm, A prime. BC is A prime B, A prime C minus A prime B, and A prime B we can calculate A prime C, A C is, this is theta, then this will be theta. Then we will have tan theta is A prime C, A prime C is X. Similarly, A prime B will be H for beta, and your BC will be H of cot theta minus cot beta. So the weight of the wedge, half of H into H of cot theta minus beta. Okay, you can write this as gamma beta H square. Okay. And when we resolve this weight, we will have normal component will be, as we saw, W cos theta H square theta minus beta sine. Sigma dash, you know, is NA over, this is the length, failure of AC. We can write AC H over sin theta will be H over AC. Okay, H over AC will be H over sin theta, and sigma dash will be gamma H over H in theta sin theta will be. So basically, what we will get is sigma equals of gamma H theta means theta cos theta. Similarly, you will get your mobilized shear strength is gamma H or theta minus theta sin square. Now, factor of safety, even, as mentioned, that if you need to calculate the critical factor of safety, it will be lowest. Like it, you have to calculate the uh, properties of the slope just at the beginning of failure, in which the tau m, you take factor of safety 1, this is the limiting condition, and factor of safety 1 is your limiting condition for you to calculate your critical slope angle, and thus you take tau is equal to tau m. You took tau as c dash plus sigma was half of gamma h sin theta cos theta equals, this is your mobilized shear strength, gamma h for theta theta sin theta. Okay, so from here, what we do is we calculate the value of mobilized friction cohesion. This is the final value that we get. I'm writing it with some simplifications. You can calculate. So basically, what this done is, um, what we do here is we want to calculate the critical uh, value of theta in at which your slope is just failing. So that what we do is we calculate the minima of this function by by this by equating this to 0, and from that we get the suitability number, Taylor suitability number, which is gamma h equals CD equals gamma h by 4, 1 minus cos of beta minus I over sine beta. Okay, and your critical height of slope, given that you know the strength of your, you know the maximum C is 4 C dash over gamma sine beta cos phi 1 minus cos of beta minus. So based on all this, we have been given this question to calculate a cut is to be made in the soil having gamma of this C dash and phi dash. Side of the cut slope will make an angle of 45 with the horizontal. It has been given that beta is 45. And what should be the depth of the cut slope that will have a factor of safety of 3. So factor of safety has been given. So what they're saying is that uh, this was what it actually means in field is that we have a soil here and I need to make a cut to a certain depth, and I'm not making a vertical cut, I am making a cut at an angle, making a cut at an angle of 45 degrees here. So how deep should the cut be so that the factor of safety of this slope that I am giving to the cut is 3. Okay, so this is basically an excavation. You are excavating this part out and you are holding the excavation based on this slope, and you want to excavate only up to a height till which you get a factor of safety 3. So how do we do that? For a trial surface, we have been given a trial surface AC. In the slope, H is 5 meters, beta is 55 degree, theta is 35 degree, and gamma. The shear strength parameters of the soil are this and this. Determine the factor of safety for the. Okay, so there are two questions. One question is that if I take this trial surface, what will be the factor of safety? And the other question is, what should this height be for the factor of safety to be 3? Okay, so let's start. We have been given phi dash is 15 degree, C dash is 8.75 kilonewton per meter. So if Fs equals 3, we assume Fc, Fy both be equal to 3. Fc is, while Fy is based on this to get a mobilized cohesion of 58.75 over 3, get mobilized friction. Is there a question? Anybody? So based on this, let's calculate. Check. Okay. So what we have been given in Kalman's method is so these are the mobilized values that we are using here. CV was 9.58, gamma was 16. This will be your critical height. Just include it. This will be 7.03 Newton. So what we are saying is that at h equals 7.03 meter, this failure slope, this slope of 45-degree angle will have a factor of safety of 3. Now, another trial slope has been given to us in which we have been given the value of theta already, and we need to calculate the factor of safety for this. So right now we were calculating the value using the mobilized shear strength parameters. Okay, so we were given a slope and we were to calculate h. We have been given this one formula, isn't it? So we were assuming that the failure will take place along mm, the C and phi values which have been mobilized. Like we were fixing these values here. Okay. Now, in this second case, we have been given the theta value itself, and what we can do is we can calculate the mobilized shear strength directly. This was cot theta minus beta times sine square theta. If you remember this. In planar failure, we calculated here half of gamma h cot theta minus cot beta sine square theta, isn't it? So this was the mobilized shear strength. Here we took the assistance of the mobilized friction and mobilized tan to calculate the mobilized shear strength. Here we are simply calculating it from the theta that has already been given. We don't need to calculate the CD or CM. Tau will be half of 17.5 into 5 into sine of, let's say, in this case, beta is not 45, it's 50, given in the question, and theta is 30. Okay, this is 10 point mobilized shear strength. Now your shear strength is C dash plus sigma dash tan. Your sigma dash equals half of gamma h theta minus theta into sine theta cos theta. Let me tell you what this is. Sine 30 sigma dash will be 96, and your shear strength will be C has been given like the values that have changed. So height is about 10 meters, 5 meters. Then we have beta is 55 degree. Theta is 35 degree. Gamma is 17 kilonewton per meter cube. Shear parameters C equals 25. Excuse me, 26. We need to calculate the factor of safety. This is the change. I'll make the changes, required changes in the PPT. Building it in the okay. This is C dash plus sigma dash tan phi dash. This will be 25 plus 6 into tan of 26. Six. This will be tau of kilonewton per meter square. Then the factor of safety for the trial will be 32.3 over 10.8, which is this is the factor of safety for this particular trial. Okay. Excuse me. So the third type of question, the third type of analysis that finite slopes can have is if we assume that the failure surface is circular. So we assume parallel, we assumed planar, we assume circular, and then there are methods in which you don't assume a shape, assume non-linear shape. So planar method is your Kalman's method. In your circular method, you have Fellenius Swedish circle method. In non-linear methods, you have your uh, Bishop's method, Spencer's method, Morgenstern Price method. I discussed them in the previous class. So, mass. So, yeah, is there a question?
Ma'am,
Yes, please.
when will this type of complex question will come in exam?
No, 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 no. I don't think so. This is just for the exams. You just need to focus on the lectures,
20%.
and you need to focus on the lectures and the tutorials and anything that is covered in the class. So basically, as I am a TA of this course, some of the courses that we are the TAs for, we are given particular assignments that we have to discuss in the problem solving week, and some courses are in which we have to prepare our own assignments. So in this case, I had to prepare my own assignments, and I tried my best to um, tried discussing all the aspects of all the topics, which might have been a little bit out of scope also sometimes, based on the this is the first course of geotechnical engineering. But yeah, my for the exams, you purely focus on the PPTs and the this thing. Whatever I teach in my class in the interactive session, that is maybe something more that we are discuss, something more we want to understand. That will not be part of the questions. Yes, I will upload the remaining PPT. But I think that my classes and my PPTs will be of more help to you for understanding the topic and understanding the concepts, rather than helping you in the exams, because I am not um, affiliated in any way in with how the questions or how the syllabus or how the contents of the PPT. Okay, so how the course is designed. Basically, I am not a part of that. That is why I mentioned that the questions will be from the makers of the course. I'm simply an external TA. Okay, so further, okay, so this is the okay. We discussed this last time. This is the phi equals 0 case in which we take clay soils and we are performing undrained tests, and for undrained tests you will get phi u equals to 0, and in these you want what you want is you want the location of this slip circle. Okay, so what we do is this is the weight of your failure block. This hole is your failure block, and W is the weight of this failure block. Okay, so W will be the weight of area A, B, C, isn't it? Into gamma. You'll have the failure is taking place in this way. So you will have a moment. Like this will be rotating. You'll have a moment at the center. So the disturbing moment will be, if this is your W, you resolve it perpendicular, you resolve it tangentially. So this will be your disturbing moment, tangential normally. Tangential force multiplied by this radius will be your disturbing moment, isn't it? So if this is your, let's not resolve it for now. Let's say that this is the, so the moment will act like this. Let's say that this is L1, which is the CG of center of gravity of the weight for this block. The disturbing moment will be uh, W times L1. Okay. And in case you had a failure surface like this, you would have had W1 times L1 minus W2 times L2. Let me show you this. In this case, you will have a disturbing moment of W1 L1 minus W2 L W1 L1 minus W2 L, and the resistance, the shear strength is acting along this failure surface, isn't it? CD is acting along, and we are assuming that this is pure clay. So let us say, assume that a unit length of failure surface has resistance of CD dash, a unit length as a resistance of CD dash. So the total resistance will be CD in length of failure surface. I've actually discussed this in the previous class, so I will not go into much detail again. All we need to know is that we calculate the moment, the driving moment and the resisting moment, and the factor of safety will be equal to the resisting moment over the driving moment, and that is your total this thing factor of safety will be W1L1 minus W2L2 over R square theta. Okay. Uh, so the uh, uh, next thing. So this actually what we are getting is for equilibrium, driving moment is equivalent to resisting. Your driving moment is CD square theta, and your resisting moment is W1L1 minus W2L. From this, you can calculate your value of CD. Okay. Okay. So once you know the mobilized cohesion, you can calculate the factor of safety as Cu over CD. Okay. But the R value was chosen arbitrarily, you know. What will be the R and the uh, theta value? You have to uh, calculate that, and we have some uh, charts for that. For critical surface, we have a minimum Cu. So we can make a number of trial and errors and calculate the minimum factor of safety thus obtained to get the critical surface. Analytically, they can be solved using your Frobenius and Taylor's method, in which CD has been given as gamma H M. This is the stability number, and we have been given uh, some charts. So you know beta, and you calculate the stability number, and from this chart, for example, stability number is zero point 0.1 and your beta is 55. So 55, let's say 30. Your beta is 30, you calculate your stability number. Sorry, I was saying it in reverse. You calculate your stability number, you will get your M, and then you calculate your gamma H times M is CD. These are the two ways to calculate your CD, and then you know your safe. Okay, So I think that is it for the questions. Now you can have, if you have any question that you want to ask about the course, we have 10 minutes and we can discuss any questions you want. Any questions? Yeah, if there are no questions, we can then end the class. This is the last class of the course, and I wish you all the best for your exams and also for your future. Any questions? Okay. Thank you very much, everyone. All the best.